I'm going to talk about the Lorenz system a little bit. And so I prepared this actually like whatever, 2-3 pages written, and show you some numerics, right? Some simulations of the system, okay? And then we move on to the next item, what we want to do today. Okay, so this Lorenz system is actually famous. That's why I wanted to show it to you. It's a very simple model that kind of catches the chaotic nature of our weather, of the weather patterns, okay? So it's a simplified model of atmospheric convection. You know, I remind you that that means that, you know, convection is when the heat goes up, right? You know, so it's about pressure and temperature, and then it comes back, you know, the hot air goes up, the cold air comes down, and this motion going all around. Okay, so this guy, Lorenz, I think in the late 50s last century. Oh my God, that seems so far away when I say it like this. Huh? Yeah, it's weird. Okay, so, you know, from the equations of fluid mechanics, because, you know, the atmosphere with the heat, you know, is modeled by in fluid mechanics, you know, anyhow, he derived this very, very simplified model that you see here in XYZ. And well, just as an idea, X is the rate of convection, Y is the horizontal temperature variation, Z is the vertical temperature variation, and we don't get into the modeling much, it's just as an idea. And then sigma, rho, and beta are some given parameters that are strictly positive. So what we already could do, right, if we would take our time, but I already kind of do it for you, okay, and it's, as I said, it's a classical subject almost in dynamical systems, is to look at equilibrium and stability. And having parameters, you know, there might be things that are changing. So indeed, if we're looking for the equilibria, when we solve the system, you don't have to write this actually, you know, it's, you can write it after if you want to. We get, you know, two cases. One is for when rho is less equal than 1, there is just 0, 0, 0 as an equilibrium. So there is no convection. Remember, X is the convection rate, okay? And then when rho is greater than 1, there are two equilibria that are non-trivial, they're non-zero. So now if we're to study stability, what we do what we have to do. We do the linearization, right? So, you know, as I taught you, we can do the linearization at a generic point, and then we substitute the numbers for the equilibria. So for the case when rho is less than 1, it's just that 0, 0, 0 is an equilibrium. We put it in, we do an analysis, and we deduce, oh, you know, there is an eigenvalue that has the real part positive. So there you go, this equilibrium is unstable, all right? And then for a rho greater than 1, there are the other two values, blah, 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 put the machinery to work, compute eigenvalues, whatever. We end up that if this condition is fulfilled, right, then this equilibria, right, this non-trivial equilibria are stable. So why is this system interesting? It's because it displays what we call, and I left on purpose there a space, it displays a strange attractor. Here, I'm gonna write it, strangers in the night. Okay, strange attractor, okay? Now, what is an attractor is exactly what it sounds like, is a point in the phase space, okay, like an equilibrium. It could be a bigger set, could be a curve of some sort, right? So it's a set to which, now, so let's say this is the simplest example, an equilibrium that is stable. It attracts, right? So all the, it's like a sink, like we did it, you know, for our two-dimensional system. So for instance, this could be a stable equilibrium, okay? But it could be also, you know, something like, here, I'm gonna flip the page, an attractor could be a periodic orbit, like a, you know, something that repeats itself. Okay, so here I'm going to make it like a circle. Well, it doesn't have to be necessarily centered in the origin. So let's say this is an orbit that comes to itself all the time. We didn't do this, we didn't study this. We'll touch upon a bit later. But the thing is that, you know, it's, you can have, you know, this could be an attractor as well, because you can have, you know, the orbits outside, right? And inside going towards this special circle. I should make it with red because it's like another type of, you know, would be like a higher dimensional equilibrium if you want, okay? That's an interesting way to put it. Okay, so this would be another attractor, right? So the orbits are kind of wrapping and tending towards this set, okay? Now, why would this one display a strange attractor? I don't know, but I can show you the attractor, okay? So if you actually Google, so I'll switch now to my screen. Okay, so there you go. So if you actually Google Lorenz system, you're going to find the big wiki page. And here is, you know, what I'm talking about. So this is a kind of a set, right? No, not okay. It is a set, okay? The butterfly effect, right? So it's strange because it's not, okay, it doesn't have certain qualities that's usually, you know, equilibrium. It's not a compact set. There is really weird stuff going on. Okay, I don't want to get into details. And another thing I wanted to show you. So this is for certain choices of the parameters that, you know, we talked about rho, sigma, and beta. Okay, and then for other choices of parameters, the system displays what is called chaotic behavior. Now, this is actually weird as a concept in itself, because this is a deterministic system, meaning that if we know the initial position and velocity, you know, for this one would be just the initial data, right? So look at it, it's an ODE, we know the initial data, okay, like x in 0, y in 0, z in 0, fix the parameters to be 1, 5, 7, doesn't really matter, okay? And then what is going on, what is this deterministic chaos? Deterministic chaos is we cannot really say where the orbit will be further, okay? So two orbits that are starting close, you would expect that they would kind of stay close, but actually they can be anywhere in the phase space later, okay? So it's something that you would expect that doesn't exist. Chaotic behavior with no quantum effects is something that, you know, it's hard to understand in a way, but, you know, that's the thing. The underscores, the physical system can completely, can be completely deterministic and yet still be inherently unpredictable, even in the absence of quantum effects. Okay, so you cannot even see it really. So I repeat this idea that, you know, you start in a point and then you will find the position, the orbit of this point, you know, that later it can be anywhere in the phase space. And two things that start close don't have to stay close at all. You know, they could be intertwined and whatever. And now with respect to the chaotic attractor, here I got it on Maple, right? See, they have actually, right, in the help of Maple, if you Google Lorenz attractor, you're going to find it. And here's the system. Okay, so I can try to make it bigger. There you go. All right. And then they offer us the simulation for different parameters. Okay, so here I was playing earlier. So this is for rho like a 10, but then if you increase, you're gonna get, here it is, the strange attractor, right? And you can play with the parameter on it and see how it changes. Okay, so the butterfly effect. So the butterfly effect is like, oh, is that thing that a butterfly spreads its wings somewhere in South America, and later, because of that spreading of the wings or flap, okay, you're gonna have a hurricane up in North America. Ta-da! Little things create big changes. It is possible. Okay, so that's why I wanted to go over this system. Of course, we will not do more than equilibrium and stability. I mean, I showed you it's standard, straightforward calculation. Okay, but yeah, I just wanted to show you this. And with this being said, I'm gonna move on to the subject of the day. So I'm gonna switch back to my, okay, there you go. And draw a line here and start what we're gonna do for the next 2 lectures or so, which is persistence and bifurcations for nonlinear differential equations. Introduction to, so I'm gonna write here persistence and bifurcations and bifurcation. And nonlinear ODEs, well, introduction to, okay. So I'm gonna start with the inverse function theorem. So I'm going to start with some calculus. Okay, so inverse function theorem 1D. Okay, so 1D because you did it in calculus 1, and it's one of those things that you do it fast and then you're like, okay, sure, whatever. I don't know if you did maybe 2 exercises on this probably in your calculus course. That would be my guess. So it's something like this. Okay, so if we have a function that is defined on an interval, an open set in R goes to R, and this function is continuous, differentiable with the derivative continuous. So this is a C1 function. Here I'm gonna make here a thing. So C1, let's say of D, is the set that contains all functions, let's say from D to R, where F is differentiable and F prime is continuous on D, okay? So in case you haven't seen this kind of notation. So that means C1. C0 would be a function that is just continuous. C2 would be a function that has first derivative, second derivative, and the second derivative is continuous. C3 and so forth. Okay, so in principle, if we say Cn of D, C refers to the nth derivative that is continuous in nth derivative, and this is the nth derivative, right? So it's just a notation, all right, in case we use it, but we use just for C1 in this course, okay? All right, so here is a function that is C1 on some interval, open interval in R, okay? And then we have that the derivative at some point A is not 0. And let's denote F in A to be B, okay? Then there is, okay, so I'll start with these maths notations, huh? A neighborhood of A, a vicinity of A, an interval about A, okay? And there is a neighborhood about B. I'll have a picture though, so the picture is 1,000 words, huh? Okay, such that there exists F minus 1 defined on V goes back to U, and this F minus 1 is C1 on V, and F minus 1 derivative in B is 1 over F prime in A. Okay. So let's digest this one for a second, right? What does it say here? Okay. It says the following. If I have a function, okay, so maybe I should draw here some simple function. Okay, so here is a little function. Okay, and let's draw a function here. Okay. And at some point, okay, so this is a nice function. It's differentiable, right? So it's smooth, it's nice, it's rounded, doesn't have any corners, right? It's continuous and doesn't have any corners. Okay, any rough spots. Okay, and here are two, you know, a point A on the x-axis if you want, and B is the value of F in A, okay? And this theorem is saying the following. Look, if I'm taking the derivative here, right? The derivative, what is the derivative? Is the slope of the tangent graph to the graph at the point. Okay, all right. So the slope of the tangent line to the graph. Okay. So if this is tilted, right? So it's not horizontal. So, you know, the F prime in A is non-zero. Okay. So it's not horizontal, it's tilted. What this theorem is telling us, it says, look, then there is a neighborhood of A. So this is in green, this is the U, okay? And then there is a neighborhood of B on the other side. Okay, so I'm trying to make it as much as and obviously this V here it is. It's a kind of the image of U, okay? And, you know, then there is a neighborhood of A and a neighborhood of B for which, you know, F minus 1 exists. So there is the inverse of this function. And moreover, the derivative, right? The derivative of the inverse at the point is 1 over F prime in A. And you're going to see, so what? Well, let's see an example, right? Okay, so let's see how we apply this. Okay. I'll say slowly, we'll get there somewhere. Okay. So, for example, okay, let's say we have f of x equals 3x squared plus ln x. Okay. And let's take a to be 1, and then such, you know, f in a, which will be the b, will be what? Will be 3 plus ln of 1. So actually b will be 3, yeah? And then I'm computing f prime in A, which is f prime in 1, okay? So what is this? Oh, this will be 6x plus 1 over x, taken at x equals 1. So this is 6 plus 1 is 7, it's non-zero. Yeah. Then, without computing what is the inverse, I don't know what it is. I actually cannot invert this function, right? So why do I say I cannot invert it? Okay, you guys, to invert the function, we would have to solve this one for x, right? Solve for x. Yeah, right. You cannot solve it for x. This is an equation that cannot be solved explicitly, okay? All right, but I don't need to solve it in order to tell you, well, there is a neighborhood of 1 and a neighborhood of 7 around which, you know, these guys, this f minus 1 exists, comes from b goes to u. So such that not only that exists, it's even, you know, C1 on this. So this f minus 1 is differentiable and the derivative is continuous, right? This is what it means, C1. And I can tell you what is the derivative in 7. The derivative of f minus 1 in 7 is 1 over the derivative of f in 1. Okay, so here the derivative of f minus 1 in 7 in this case will be, what am I saying? Not in 7, but in 3. But, okay, right? So this is 3, right? Because there's the b is 3. I'm getting, yeah, good. So this would be 1 over 7. Yeah. Okay. Without knowing what the inverse is, this is the key, right? I can just, you know, so that's what it is. Okay. Okay. All right. Now I should show you why it's not working when this is, right? At least, you know, sketch it. So here is the picture, right? So we had a picture, what did I do here? Something like this here, right? Oh, okay. Okay, so this was with the derivative non-zero, okay? Whereas with derivative 0, right, would be something, oops, okay. Okay, so I would have this point, let's say, where the derivative is 0, okay? And then if I am to try to do the same thing, this would be A, right? And this would be the B, okay? And I'm not sure how to take, you know, this, if I'm looking at the neighborhood of A, like we did in the other side, right? Here is a neighborhood of A. Actually, yeah, I'm gonna try to make it more suggestive. Just a second, guys. Because this doesn't have to be, hey. Okay. So I'm taking this one out and I'm putting it in a bit. So you don't say that I'm something like that. Okay. So here is the neighborhood of A that is completely, so this would be the V, right? But the V doesn't even include the B, huh? So you can see how this thing, it doesn't really work anymore. That's what I mean. Because, you know, if I want to turn it, right, I would have, the value of A is not even in the interval that I'm considering. That's one reason. I could make other pictures again, you know, that kind of show us that we cannot invert there, or, you know, something wrong is happening. So what we know for sure, though, is that if the value here is this slope is non-zero, then we can invert for sure. So let's just play what we know for sure. Okay, fine. All right. Now, the next level is like, okay, is this thing just for functions in 1D, or does it work for higher order functions, like for domains in R2 or R3? And the answer is, of course, you know, it's generalized. Okay. So here it is, inverse function theorem, ND, okay, in Rn. So this one goes like this. Let's take f in a domain in Rn, goes to Rn, right? Could be R2 to R2, R3 to R3. And then f is, again, differentiable with the derivative continuous, okay? So on D, all those partials are continuous, okay? All right, and then we know that the determinant of df at dx, okay, at some, so I'm gonna write here, at some point A, where A obviously is in D, right? So I'm making them vectors just to make a point that this is in Rn, yeah? All right, so it could be like XYZ or something like that, right? Okay, then in these terms, conclusions are kind of the same for the time being. There is a neighborhood of A and a neighborhood of F in A. Let's call it B. So let's call here F in A. Let's call it to be B. Okay. Such that F minus 1 defined on V goes to U exists, and F minus 1 is C1 on V. And now comes that part with the inverse, huh? So, and here is the cute one, okay? The derivative of F minus 1 at Y, right? At the point Y equals B equals the derivative of F at X. This is the Jacobian, if you want, okay? As a matrix taken, right? The inverse as a matrix at X equals A, okay? So this is the theory, okay? So instead of having 1 over, right? So if we have a number, for a number, 7 minus 1 is 1 over 7. For a matrix, right? If we have A minus 1 is like 1 over A, okay? I remember I did this in class with the linear algebra last year. I was emphasizing this, right? So because for numbers, if we have 7 times 1 over 7 gives us 1, right? So that's the inverse. Whereas for matrices, right, if we have A minus 1 times A is the identity in that space, let's say N if it's in Rn, right? And by the way, it has to be also the other way around because the matrices sometimes they don't commute, but the inverse is the one that commutes with the original matrix, okay? So this is like a side note just to make sure that you guys, you know, we're on the same note here, okay? So when I say here, this guy here, this is the Jacobian matrix. Okay, and actually I'll have an example for you, okay? Okay. So let's see. Example, okay? We have F defined on R2. So I'm taking this to be R2, goes to R2. F of X and Y equals sine of X squared plus Y, and then X squared minus Y squared, okay? All right, that's the function, okay? And then we're gonna take A, that A point, that I put it as a vector if you want, that's root pi and 0. Okay. So B is F in root pi and 0. So is 0 and pi. Yeah, good. Yeah. Okay. And now let's see what it is. So the question would be, okay, do we have an inverse? And what would be the derivative of an inverse? You can ask me, why are you doing this? Just because it has to be done. Okay. All right. So here is df dx, okay? So where x here as a vector is actually x and y, little x and little y. Okay, sorry about the notation, but that's how it popped out, okay? I should have put maybe x1, x2. Okay. All right, so what is this? Okay, so this is the Jacobian matrix, okay? So we do df dx, okay, df1 dx. Okay, maybe I should do it like this here rather than. So it's d dx of sine of x squared plus y, and then d dy of sine of x squared plus y. Everybody loves me because it's just calculation. I know this, okay? d dx, x squared minus y squared, and then d dy, x squared minus y squared. Ta-da! Okay. So what is df dx? Okay. Let's see. Okay. So we would have a cos of x squared plus y times 2x, cos of x squared plus y times 1, 2x, and minus 2y. Okay. And now if we calculate this at the point, so x is root pi and y is 0, right? So this is at x is root pi and y is 0. So we get the df dx at, right, how should I write this? I put them on the vertical, now I'll put them on the horizontal, but you get it, okay. So this is minus 2 root pi, or when we calculate, minus 1, 2 root pi, and 0, okay? Good. And now we do determinant of this thing. Okay, so it's root pi and 0. So obviously the determinant will be 2 root pi. So it's not 0. Oh, so if it's not 0, then we can invert f in a neighborhood of A. Okay. And then we will also know what is the derivative of f, the Jacobian value at the inverse there. Okay, so let's write this. So then there is f minus 1. No, okay, so first the neighborhoods. So there is a neighborhood of root pi and 0 and a neighborhood of 0 and pi. Yeah? So this is, there's the A and there's the B, yeah? Okay. And f minus 1 defined on V goes to U exists, okay? And f minus 1 is differentiable with the derivative continuous on V, and the derivative of f minus 1 at the point 0 pi, okay, so at y equals, if you want, 0 pi, equals the inverse, right, of the matrix that is the derivative at A, right? So in this case was minus 2 root pi, 0, minus 2 root pi, minus 1, 2 root pi, and 0. Okay, which we can calculate. Okay, you can use maple, whatever, right? So we end up with df minus 1 dy at y being 0 pi, not 0 over pi, 0 pi is a point. Okay, equals, when we do the inverse of that one, we get here a matrix as such. There you go. So it's knowledge without doing, you know, everything, anything called explicit.